Hi, welcome back to the playlist on carbohydrates. Alright, so in this video we're going to go over something that might be a little scary at first, but hopefully I can clear some things up and make it a little less scary. And that's stereochemistry of carbohydrates. Now, when you did organic chemistry, one of the topics you probably did at the beginning of Organic 1, first semester, so you probably did a lot with enantiomers and diastereomers. Okay? Usually in biochemistry, and I know at the school that I took it at, they're not going to ask you things like, oh, determine the relationship between these two carbohydrates, okay? They're not going to do that. Nobody does that, all right? But you at least need to know the different kinds of stereoisomerism we can have. That way, we can have a way to qualitatively compare two carbohydrates, okay? So before we actually get into diastereomers and enantiomers, I'm going to go into something called Epimers and Animas. Okay, and the reason I'm going to do this is because I think this order that I have them is the most logical order to do these in. Okay, so what is an epimer? All right, so first thing I want to do before we do anything related to stereochemistry, we need to talk about one thing. What I'm going to do is I'm going to draw some generic carbohydrates. Okay, so, oops, let me do this in white. Make sure I have the right color, white, all right. So when I draw these, I'm actually doing this in something we talked about in the last video called a Haworth projection. This would be a 6-membered carbohydrate. It has 6 atoms in the ring. And we also do one that has 5 members in the ring. Like that. Okay. So what we're allowed to say with these is that with each of these atoms, with the exception of the oxygen, we're allowed to have a group that's up. So I'm going to draw these up. We're allowed to have groups that are up, okay? And then we're also allowed to have groups that are down, okay? And the same thing is going to go for the 5-membered rings. We're allowed to have groups that are up, like this. And we're also going to have groups that are down, okay? Like that. If something like this, if we don't indicate one of them, then we're just assuming it's a hydrogen. So that would be a hydrogen. We're not indicating something going up. That's a hydrogen. That's a hydrogen, and this is a hydrogen. So kind of the same rules from drawing normal structures in organic. If something on a carbon is not indicated, it's assumed to be a hydrogen. Okay, but the point is we can have groups going up and we can have groups going down. Now, when you're dealing with carbohydrates, like these two right here, they're often polyols. Remember we talked about polyols. What is that? Ol is the suffix for alcohol, so it means that they have multiple alcohol groups on them. They usually have many. Okay? For example, this one has 1, 2, 3, 4, 5 alcohol groups on it, so they have many of these. And ordinarily with carbohydrates, the position of the alcohol, whether it's up or down, determines which carbohydrate it is. All right? So I want you to notice something very quickly. All right, let's look at this. I'm going to number these carbons because the numbering is very important. When you number them in the ring, you can number them really any way that you want. So what I'm going to do is I'm going to designate this as 1, 2, 3, 4, and 5. And when you do it on any other that looks the same, you have to be consistent. So 1, 2, 3, 4, 5. All right, so now we have a consistent way of talking about these. All right, let's look at carbon 1. What's the positions of the OH on each of them? Well, they're both going up. So that's the same on both of those. I'm looking at position 2. How do the OHs differ? They don't. They're both going down. If I look at position 3, how do they differ? They're both going up. I'll switch to 5 for obvious reasons. If I go to 5, it's not a direct hydroxyl, but it's still a group, right? What's the position of that, of this thing right here? I'll go ahead and circle it. This is actually called a hydroxymethyl group. What's the position of that? It's both going up, right? But look at position 4. What do you notice on that? On this left one, this carbohydrate on the left is actually, it's not L, this is actually D-glucose. Glucose. Like, let me go ahead and write out glucose. This hydroxyl on the 4 position glucose goes down. On this one actually happens to be galactose. On 4, it goes up. So what do you notice? The only difference between these two sugars is position 4, meaning that there's only one carbon whose stereochemistry differs. When you have 2 carbohydrates and they only differ by the position of one hydroxyl group, that is the one at position 4, they're termed epimers of each other. You could say they have an epimeric relationship. Okay? When you have only one OH whose position flips across the ring, one of them only, they're termed epimers. Okay? So let's potentially, I'm going to do this. Let me go ahead and move this for a second. I'm going to move that. I did not think that would happen. Let me go ahead and fill this in. All right. Let me potentially draw another epimer. Let's draw another epimer of glucose. Okay? So what is my definition of an epimer? They only differ at the stereochemistry, or the hydroxyl flips only at one carbon. So let me draw an epimer of glucose where the second position flips. Let's flip it at the second position. So I'm going to keep this OH going up like this. Here the OH goes down on glucose, so if I'm trying to draw an epimer at the 2 position, I'm going to go this one going up, see how it's flipped. This third one goes up, I'm going to keep this one up. Fourth one goes down, I'm going to keep that down. And then this one goes up. This sugar right here, this is mannose, one you may not have heard of. Okay? So, if and I'm going to do this, let me do this in actually yellow. So notice glucose has this 2 position going down, whereas mannose has the 2 position going up. And I can even go back and rewrite the numbers in. This is 1, 2, 3, 4, and 5. Okay, so hopefully that makes sense. Now a question. Glucose is an epimer of galactose. Why? Because the only difference is the position, or is the position of the OH at the 4, right? 4th carbon. Glucose is an epimer of mannose. Why? Because the only carbon that they differ at is 2. On glucose, the OH goes down on 2. On mannose, the OH goes up on 2. Are galactose and mannose epimers? No. Why are they not epimers? Because they actually differ at 2 positions. Notice, here on galactose, the OH goes down, and on mannose, it goes up. But also at the 4 position, the hydroxyl on galactose goes up. On mannose, it goes down. They differ at more than 1 position. It's 2 positions. So mannose and galactose are not epimers of each other. But galactose is an epimer of glucose, and mannose is an epimer of glucose. So the key here is epimers only differ at the stereochemistry at 1 carbon. Only 1. Now, a really useful one to go into now is an anomer. Now, one definition first. What is an anomer? An anomer is an epimer, but the requirement to be an anomer is the 1 position that has to be flipped is always the 1 position. All right, so 1, 2, 3, 4, and 5. Okay? So this position that I've highlighted in purple, that's the one that has to be flipped for this to be an anomer. Okay? If I flip the 3 position, let's say they differ at the 3 position, that's not an anomer. It's still an epimer, but it's not an anomer. So an anomer is a special form of an epimer where the position that's flipped is that 1 position, that one that's highlighted. Okay? It's always that 1 position. All right? Now, where does the term anomer come from? Well, this position that's highlighted in purple, this is what's often termed, it's given a name, it's the anomeric carbon. And the reason that carbon is special is there's actually some reactions that happen at that carbon that occur non-enzymatically. And we're going to go into that in another video. We're not going to do that here. But suffice it to say, this carbon has some chemistry that goes on, and it's given the name anomeric carbon. So because you can flip the position at that, flip the stereochemistry at that position, the anomeric carbon, they're given the name anomers. So an anomer is an epimer, but the stipulation is the stereochemistry can only be flipped at that position. And that would qualify it as an anomer. All right? So for another form of an anomer, let's look at this. All right? Let's look at another anomeric carbon. So this is a 5-membered ring. This molecule right here, this is ribose. You may have heard of ribose. It's a component of RNA. So let's number these carbons. This one, this purple one, it's generally the one right next to, generally the one, when you usually draw these, it's going to be, if you draw them like I do, it's always, it's clockwise from this oxygen. That's going to be 1, 2, 3, 4. Technically, this oxygen would be 5, but I don't really count that. Okay, so 1, 2, 3, 4. And this is 1. So this right here, this is the anomeric carbon. So what would be the anomer of this form of ribose? How would I draw the anomer? Well, I would want to flip that configuration at the 1 position. Right here, I want to flip that. So am I going to flip the 4 position? No. Am I going to flip the 3 position? No, that still goes down. Am I going to flip the 2 position? No. Am I going to flip the 1 position? Yes. Because by definition, the anomer is the epimer that differs at the 1 position. Okay? It's going to differ at the 1 position on the ring. Okay? The 1 position on the ring. If you're wondering about why this gets the 1 position, the reason is because if you actually think back to your DNA stuff and RNA stuff, in ribose, this is, remember, 1', 2', 3', 4', and so forth. Okay? That's why it gets those names. But you don't actually have to look at it that way. I generally just draw it like this and say the one clockwise from the oxygen in the ring is 1 by default. Okay? And you can number it any way you want, but generally in all of these, the anomeric carbon is going to be directly right next to that oxygen. And actually the reason that the chemistry happens there has to do with this oxygen. Okay? But hopefully that makes sense of what an anomer is. So I think it makes a lot more sense to talk about epimers and anomers first. And in the next video, I'm going to cut it off right here, we're going to go into diastereomers and enantiomers. And those different kinds of carbohydrates. Okay, so this concludes this video on stereochemistry of carbohydrates. We're going to finish this topic up in another video after this, so keep watching for that. Thank you so much for watching this. I hope it made sense. Make sure to like this video and subscribe to the channel for future videos and notifications. Thank you.